Okay, so why are we interested in this Poincare series? Because we can use this to define so this Patterson-Sullivan measure on the boundary as follows. So first of all, we look at what's called the limit set of gamma. And this is the closure of the orbit of x minus the orbit of x. Okay, so this is a subset of the boundary. You take the closure in x union boundary. So that is compact because x is proper. So that's something I didn't say. So x proper means that x union its boundary is compact. All right. So we need that. Okay. So you take the closure. So this is a compact subset of the boundary. All right. And this is independent of the choice of orbit. Okay. That's not hard to show. Okay. So we're going to define a measure on the limit set called the Patterson-Sullivan measure as follows. So for simplicity, assume that the Poincare series at delta is infinite. Okay, it diverges at the critical exponent. It may converge at the critical exponent. It could converge or it could diverge, but let's for simplicity assume it diverges. Okay, this is true, for example, if well, you don't need this, but I mean, this is true, for example, if gamma is co-compact. Okay, so then what we can do is the following. We define a measure mu x comma s for every s bigger than delta. So I know the Poincare series is finite. So what I can do is I can take points of the orbit of x. And I put Dirac masses at the points of the orbit, and I weight them by the terms which occur in the Poincare series. So e to the minus distance x gamma x. All right. Okay. And so together, I want to probability measure. So I divide this by the Poincare series, 1 over PS. All right. So then this mu xs, this is a probability measure on the orbit of x, right? So I can take it as a probability measure on the orbit of x union the limit set, which is some k compact subset of x union boundary x, right? Okay. So now what I want to do is I want to let S tend to delta from above, and so then along some sequence, since the set of probability measures on a compact space is weakly compact, right? I will get a limit for some subsequence S tending to delta. So I'll just write it as S. Along some sequence, mu xs converges to a probability measure mu x, right? Yes? Yes?
Yes, sir.
Okay. And So what will the support, where will the support be? Well, if I take any ball inside X, then there are only finitely many terms of the orbit, points of the orbit there. So there are finitely many terms of this sum. And as S tends to delta, P of S goes to infinity, right? So for any finite ball, its mass will be basically a constant divided by P of S. So that goes to 0 as S tends to delta, right? Because P of delta is infinity. Okay. So therefore, the mass of any ball in the inside is 0. So this means that mu x will be supported in the limit set, right? The support of mu x is contained in the limit set. Okay? Because PS goes to plus infinity as delta, as S tends to delta. Is this clear? So I get a measure in the limit which is supported on the limit set. All right. Yes. Now
Yes.
this measure, I claim this is conformal of dimension delta for the group gamma. Okay. So before saying that, I have to say, if I take a gamma in gamma, okay. So if I look at gamma acting on del x comma rho x, right? So this is a conformal map, right? What is mod gamma prime of xi? Okay. So this is the limit eta tends to xi of rho x of gamma xi gamma eta over rho x xi eta. And now since gamma is an isometry, rho x gamma xi gamma eta, this is the same as rho gamma inverse x of xi eta, right? Because gamma is an isometry. Yes. Okay. So now what is this? This is the derivative of the visual metric rho gamma inverse x with respect to the visual metric rho x, right? So this is d rho gamma inverse x d rho x. Yes. Of xi, which is, we know what this is, e to the b x gamma inverse x xi, right? Okay, so this is the derivative of gamma, is this function, all right, of xi. Is this clear? Yes? Yes, is this okay?
Yes, sir.
Okay. Now I want to look at so to say that, see, what I want is that mu x of gamma e is equal to integral over boundary x of mod gamma prime xi to the power delta d mu x, right? Okay. So this thing I can write as what? This is equal to the push forward by gamma inverse, right? This is gamma inverse push forward mu of E, right? Yes. Right.
Yes.
And this is what? This is integral over boundary x, e to the delta b x gamma inverse x xi d mu x of xi, right? Yes. So, sorry, this is not integral over boundary x, integral over e. Sorry, this is integral over e, not integral over boundary x, integral over e. Sorry. So this is for all e in boundary x. Now, what this means is basically, so if I replace gamma by gamma, gamma inverse by gamma inverse, so what we want is that for all gamma, gamma star mu is equal to what? Is equal to a function e to the delta b x gamma x dot into the measure mu x, right? Right? This is what we want to prove then. Is this clear? Yes?
Yes.
Okay. Now we prove this by passing to the limit. So we look at gamma star of mu xs, right? Okay. Now, what is gamma star of a Dirac mass? Delta gamma x, delta x. Oh, sorry. Maybe I shouldn't use gamma. Oops. Okay. So let me call this for all alpha. Okay, fine. Then it's all right. Yeah. So for all alpha. Okay. Right. Alpha star mu x is equal to e to the delta b x alpha x dot d mu x. So what is alpha star of the push forward of Dirac mass at gamma x? This is Dirac mass at alpha gamma x, right? Okay. So the push forward will be 1 over ps sum over gamma in gamma e to the minus s distance x gamma x Dirac mass at alpha of gamma x, right? Yes. Right? Is this okay? And now I make a change of variables. I put some new, is this okay? So I put now G equal to alpha gamma. I make a change of variables in this sum. So G equal to alpha gamma. So then this becomes 1 over PS sum over G in gamma e to the minus distance x. So gamma becomes alpha inverse G, right? X alpha inverse G x delta Gx. Okay. So this e to the minus this, what I do is I write this as e to the minus s distance x gx. Okay. Into okay. Right. So yeah. So into e to the minus s distance x alpha inverse gx minus distance x gx. Okay. All right. And the whole thing into delta gx sum over g in gamma 1 over p of s. Okay. So this is what I had earlier. Now this thing, what I can write this as, this I can write this as some function phi of gx, okay, where phi of y is what? This is e to the minus, or let me write this as e to the minus s phi of gx, where phi of y is distance x alpha inverse y minus distance xy. Okay, right? Okay, phi is a function of y. Now this on the boundary, as y converges to xi, what does this converge to? This converges to Boseman function. Okay, so wait, let me write this. This is the same as distance. So the alpha is an isometry. So distance alpha xy minus distance xy, right? Yes?
Yes.
Right? So, right. So, okay, okay, fine. Let me make this a plus, and I change the sign of phi. I make this a minus and this a plus. So I make this a minus and this a plus. So this converges as y converges to xi. This converges to b of x alpha x xi, right? By definition of the Boseman function, by what we proved earlier, right? So what do we get finally? We get that alpha star of mu xs is equal to e to the minus s phi into mu xs, all right? And this implies, by passing to limits, that alpha star of mu x is equal to e to the minus, well, or e to the plus delta phi, as s tends to delta, mu x, right? Where, see, delta is a function from x union boundary x. Sorry, phi is a function. Sorry. Phi is a function from x union boundary x to r, right? So y maps to distance xy minus distance x alpha inverse. So distance alpha x y. Okay, so this is if y is inside, and on the boundary it is b of x alpha x xi, right? This phi is a continuous function. Is this clear?
Yes.
Right. So that's it. So we get what we wanted, right? In this mu x is supported on the boundary. So on the boundary, this is equal to e to the delta b x alpha x xi mu x, right? And so that proves that mu x is conformal. Is this clear? Yes? Okay.
Yes.
All right. Okay, so now we can try and finish up the proof of Mostow rigidity. So, so once you have a conformal measure, okay, what Sullivan proves is something called the shadow lemma. So I have my x, and on the boundary, if I take a ball of radius epsilon, then for epsilon small, there exists a constant bigger than 1 such that mu x of the ball with respect to the visual metric bx xi epsilon, this is less than a constant epsilon to the power delta and bigger than 1 over a constant epsilon to the delta. Okay, this is called the shadow lemma, Sullivan's shadow lemma. And basically the idea is, I mean, if I have a ball of radius epsilon, I can use an element of the group gamma to blow this up to a ball of some fixed size. Okay. And then you use the derivative of gamma. It blows up ball of radius epsilon to ball of radius approximately 1. So mod gamma prime is roughly like 1 by epsilon. Okay. And so if I look at alpha, which is the inverse, the derivative of alpha looks like epsilon. And so then mu x of the ball, this looks like mu x of alpha of some fixed set E. And this looks like integral over E of mod alpha prime power delta d mu x. And so this alpha prime is like epsilon. So this looks like a constant times epsilon to the power delta. All right, that's the idea. Okay, does this make sense?
Yes.
Okay. So once you have this, then what you get is that mu x is absolutely continuous with respect to Hausdorff measure of dimension delta. They're mutually absolutely continuous. Okay. All right. Now you do this where gamma is equal to pi 1 m. Which is a co-compact group acting on Hn. Okay. So in this case, because gamma is co-compact, this implies that the critical exponent of gamma, so this was basically lim-sup of log of the cardinality of the orbit so I mean I'll just write it like this: cardinality of OX intersect BXR over R. And see, the number of orbit points is the number of fundamental domains in this ball, and the fundamental domains all have the same diameter, right? So this will be proportional to the volume of the ball. All right. So it will be up to a constant, it will be bounded above and below by constants times the volume of the ball. So when I take log and divide by R, this will be the same as just the logarithmic volume growth of the hyperbolic space. So this will be the same as log of the volume of the ball of radius R divided by R. Okay, because gamma is co-compact. All right. Yes. And so this now is equal to, this I know for the hyperbolic space, this is n minus 1. All right. Yes. Are you with me? Hello?
Yes. Yes.
Okay. So therefore, what I get is that my Patterson-Sullivan measure, mu x, this is mutually absolutely continuous with Lebesgue measure, right? H n minus 1 is just Lebesgue measure on boundary Hn, which is Sn minus 1. Okay. And Hn minus 1 is absolutely continuous with respect to mu x. Okay. And now my f from so if I take say now I have, say, gamma 1 is pi 1 m and gamma 2 is pi 1 n. Okay. And so for this I have mu 1, a Patterson-Sullivan measure, and for this I have mu 2, another Patterson-Sullivan measure. Okay. So these are both my conformal measures. So here's a key fact. So I have my boundary map f from Sn minus 1 to Sn minus 1, Quasi-Mobius. And the dimension of the boundary is at least 2. So n minus 1 greater than or equal to 2, because n was 3. This is where I'm using n is at least 3. This implies, this is purely a fact of analysis, that f is absolutely continuous with respect to Lebesgue measure on Sn minus 1. Okay. So this is a fact. So this implies that f star mu 1 will be absolutely continuous with respect to mu 2, right? Because these are mutually absolutely continuous with respect to Lebesgue measure. Okay. And so now I do the following. I look at the space del 2 Hn, which is boundary Hn cross boundary Hn minus the diagonal. And on this, I define a measure. What should I call it? Say M1 is this measure. It's d mu 1 xi d mu 1 eta divided by rho x xi eta to the power 2 delta. So delta is n minus 1. And M2 is d mu 2 xi d mu 2 eta divided by rho x psi eta to the 2 delta. Okay. Are you with me?
Yes, sir.
Okay. Now these are measures on del 2 HN. All right. And the thing is, these this M1, this is invariant under gamma 1. This Mi is invariant under gamma I actually. Because if I take a gamma and gamma, then what will this be? This will become like if I look at basically gamma upper star M1, the push forward. So this will be gamma upper star M1, sorry, mu1 cross gamma upper star mu1 divided by rho x of gamma xi gamma eta power 2 delta, and this is equal to this push forward, because this is a conformal measure. This will be mod gamma prime xi power delta into mod gamma prime eta power delta into d mu 1 xi d mu 1 eta. Okay. And over here below this thing, by the geometric mean value theorem, I'll get a mod gamma prime xi to the delta mod gamma prime eta to the delta rho x of xi eta to the power 2 delta. Okay, so the equality below is from the geometric mean value theorem. All right. And so these will cancel. Okay. And so this will be equal to M1. Is this clear?
Yes, sir.
All right. So these are invariant measures. And what happens is basically, you see, there's a correspondence. I talked about this in one earlier class long ago, that if I look at the unit tangent bundle, right, if I fix my base point x here, and then if I look at the unit tangent bundle V, then there's a map from the unit tangent bundle to, this is for any cat minus 1 space, I'll get V plus, for any manifold, let's say V minus, and I will have this horospherical distance. I have a map from T1x, the unit tangent bundle, to del 2x cross R. V goes to V plus, V minus, B of X pi V V plus. Okay. This horspherical distance here. Okay, so this map is a homeomorphism called the Hopf map. Okay, this is the Hopf parametrization. And what happens is the geodesic flow here gets conjugated to the flow of translations in the R coordinate here. If I move by t, right, then this changes by t, this Boseman function, all right? And so an invariant measure for the geodesic flow here, if I look at, say, m equal to x mod gamma, so an invariant measure say, I don't know, mu here, which is invariant under the geodesic flow. This corresponds to an invariant measure on T1x, which is, say, some mu tilde. This is invariant under R cross gamma. Okay, so that corresponds to a measure on del 2x cross R. So maybe let me make this gamma cross R. Yeah, sorry. So you get a measure here, say nu tilde, which is invariant under gamma cross R. And if it's invariant under the R coordinate, then it's just a measure on del 2x times Lebesgue measure on R, right? So that corresponds to an invariant measure on del 2x for gamma. Okay. Is this clear?
Yes, sir.
Okay, so invariant measures for the geodesic flow correspond to invariant measures for on del 2x for gamma. And if mu ergodic, then m is ergodic. So mu is ergodic for the geodesic flow if and only if m is ergodic for gamma. Okay, so I just want to finish this. I'm sorry we're going late, but it's the last class. Just give me a few more minutes, okay? One more meeting and I'll try and finish this, all right? Okay. So just one more meeting. Okay, thanks.